Yes, hello students. So let us continue. Let us start with the Onsager equation. Onsager equation. Sorry, Onsager, Onsager equation. So what it is? This was the scientist Onsager who actually found an equation to find the molar conductivity of strong electrolytes. So this is especially for a strong electrolytes, because we already saw one equation for molar conductivity for a strong electrolyte. Now this was actually modified that particular equation. You remember this lambda m is equal to lambda m0 minus a root c. So this was the equation we discussed before, where lambda m is a molar conductivity, lambda m0 is a molar conductivity at infinite dilution, and a is a constant with respect to an electrolyte, and c is the concentration. So this was the equation we introduced before. Now, after considering the effect of a solvent like viscosity and another factor, the dielectric constant, such factors, including such factors, Onsager modified the equation for finding the molar conductivity of an electrolyte, of a strong electrolyte. So let us discuss there what it is. Onsager equation is lambda m is equal to lambda m0 minus 82.4 divided by dt raised to half into eta plus 8.20 into 10 raised to 5 divided by dt raised to half into lambda m0, where lambda m0 is a molar conductivity at infinite dilution, and into root c. So this is the modified Onsager equation for finding the molar conductivity of a strong electrolyte at a given concentration. Well, let us introduce the terms. Lambda m is the molar conductivity at a concentration C. And lambda m0 is the molar conductivity at infinite dilution, that we will call limiting molar conductivity. What is D is all about? D is dielectric constant of the medium. And T is the temperature, that is Kelvin temperature. And one more term is there, that is eta, that is now viscosity of the medium. C is the concentration. Of the solution. So this is the way the equation for finding the molar conductivity of a strong electrolyte. You can introduce like this. Lambda m is equal to lambda m0 minus 82.4 divided by dt raised to half into eta plus 8.20 into 10 raised to 5 divided by dt raised to half into lambda m0 into root c. So we can now just simplify it, because these are constant terms, right? So this is the equation modified based on the mainly two effects, that is D, dielectric constant of the medium, and temperature, as well as the eta, which is the viscosity of the medium. So that's how Onsager equation has been introduced. You can just simplify it. Lambda m is equal to lambda m0 minus lambda m0 in minus a plus b lambda m0 into root c. A plus B lambda m0 into root c. So look at this particular equation now, where A is this part, 82.4 divided by dt ratio of into eta, so that is A for you. Okay, these all are constant, so we introduce a constant for instead of this, and B is nothing but another constant, 8.20 into 10 raised to 5 divided by dt ratio of, that is B part for you. So into lambda m0 into root c. So we can simplify the Onsager equation. Lambda m is equal to lambda m0 minus a plus b lambda m0 into root c. Look at this. This is a speciality where no, this is just an equation for a straight line equation, right? It's an equation for a straight line. So y equal to mx plus c like mod. Y equal to mx plus c, where m is the slope. Now if you plot a graph between lambda m versus root c, you actually getting a straight line. So this is now a straight line with a negative slope. You can see negative sign is there, so where m is the slope. Now slope actually now value is a plus b lambda m0. So this is the now Onsager equation. We expected to get a straight line with a negative slope. Okay, for the if you plot a graph between lambda m versus root c, where m is the constant, m is the slope here, which is equal to a plus b lambda m0. So now let us validate this Onsager equation based on plotting the graph, whether you getting the correct result or not. Let us now check it. If you talk about now validity of Onsager equation, if you plot a graph between lambda m versus root c, interesting kind of a plot that we are getting. Now actually we are getting a straight line, that's okay, but now it found to be it's going like this, but as the concentration increases, there is an increase in molar conductivity that is observed. Now if you plot a graph of NaCl, and like KCl is also giving a result like this. It is a straight line now, but at the higher concentration it has a change. So KCl, if you extrapolate to y-axis, you actually getting a lambda m0, that is limiting molar conductivity. So this is the expected graph. So I cannot dash line, I can represent as it is theoretical plot, and the thick line represent the experimental results. So if you plot a graph between lambda m versus root c, this is the way we are obtaining. We are actually expecting a straight line, but it's not. It's yes, most of the part is obeys, but now at a higher concentration, you can see molar conductivity increases with the higher concentration. That is one of the unexpected result, because now we expect molar conductivity to increase with the increase in dilution, which means decrease in concentration always favors the molar conductivity, right? Yes, it's with a decrease in concentration or increase in dilution, molar conductivity definitely increases. But now what our expectation is, with the increase in concentration, the molar conductivity has to decrease. It's obeys, so most of the part, but not a high concentration, you observe an increase in molar conductivity again. That means yes, Onsager equation is valid for strong electrolytes at low concentration, or I will say high dilution. This perfectly obeys, but not higher concentration, it shows some deviation. So that's the point you can remember about Onsager equation is valid for a very dilute solution, but at a higher concentration it show deviation. What may be the reason? You can think. Where we expect the ions to move to have a good conductivity. That why at a higher dilution or lower concentration, what's happening? The ions are more separated from each other. They are free from all kinds of intermolecular ionic attraction. We will say positive, negative, cation and anion attraction will be very less in a dilute solution. So we expect the ion to move freely, which means molar conductivity will be higher. That's the way easily you can explain. So what may be the reason? There is a slight increase in molar conductivity, higher concentration. That suggests you know there is, rather than the a cation anion attraction, a repulsive action is coming into play, because no, it's you can see concentration higher means no cations anions are more in a particular region, which means no you can expect the repulsion factor between same type of ion like cation and anion that going to be increased. That really makes them slightly free in their movements, which are reflected in the molar conductivity. Okay, now more we will discuss in the later session, because we will discuss about ionic mobility and other factors. So let us now pointed out this particular point. Onsager equation is valid at a lower concentration or high dilution. As the concentration increases, now Onsager equation shows deviation, and this is especially especially this is work for monovalent electrolytes. Monovalent electrolytes obeys Onsager equation. Onsager equation at lower concentration, or higher dilution, now as the high valent electrolyte like now CaCl2, this is not monovalent, it's higher high valent electrolyte like now CaCl2. You can see MgSO4. This is now charge will be plus 2SO4 will be 2 minus C plus 2 Cl minus. Like now this is the case where Onsager equation shows some deviation, simply because you can see the concentration of ions is maybe show some changes and also there is a increase in cationic and anionic charge will be there. That also reflects in the molar conductivity. So all about how much ionic attraction exists in the solution, that definitely reflect in the molar conductivity. If the ionic attraction is high, means ions cannot able to move. So higher the ionic charge, that will reflect. Higher the concentration, lower the concentration, moderate concentration, everything going to influence the molar conductivity. So that's the way you can understand. For the time being, you can understand like this. The Onsager equation obeys for a monovalent electrolyte, especially for monovalent electrolyte at lower concentration or higher dilution, it obeys. So that what Onsager equation is all about. So Onsager equation, especially for strong electrolytes, you can find the molar conductivity of a strong electrolyte using Onsager equation. So that's all about Onsager equation, and higher valent ions that we can call polyvalent ions or polyvalent electrolytes. You can remember that. Then now there are two effects that we are going to learn. That is first one, Vane effects. Vane effects. So this is something an interesting point which actually an evidence for the ionic atmosphere to exist, and just shows how high voltage changes the molar conductivity. It is observed that at high voltage is around 10 raised to 5 volt. If voltage is not such high voltage is provided, volt per centimeter. So such high voltage is provided, which means here two factor is playing. One, voltage is such higher that ions are getting such a high energy, so that it doesn't have the time to form the ionic atmosphere, where cations surrounded by anions surrounded by cations. Such ionic atmosphere cannot able to form because of such high voltage has been provided, which means what we can think Yes, at such high voltage it is observed that molar conductivity increases. There is no real dragging effect or retarding effect like electrophoretic effect, no asymmetric effect, nothing is coming here. Because of the high voltage, ions are free to move. Because no ions getting such high energy, they can able to break the kind of attraction that withdraws their movement, that retards their movement, that has been restricted. Which means no, at high voltage it is observed that no molar conductivity increases. At high voltage molar conductivity found to be higher. At high voltage molar conductivity found to be higher, no, simply because what actually drags the no molar conductive what actually drags the movement of ion, that you can think, which actually restrict their movements. One, especially ionic atmosphere, because cation attracted by anion, such ionic atmosphere exists there in the solution, which restrict their movement, because as the attraction is higher means ions cannot able to move freely. So what the high voltage is doing, it doesn't allow the ionic atmosphere to form. Such high such a high voltage, we talk that particular point, that relaxation time is a time for the formation of an ionic atmosphere to form. So relaxation time is we talk about ionic atmosphere to form. The time is not sufficiently enough. Ionic atmosphere cannot able to form because of the high voltage. And also dragging effect like asymmetric effect and the electrophoretic effect, nothing is coming, because the high voltage can able to break such dragging forces. So that's what now we observe, and scientist Wayne actually introduced this, that why we'll call Wayne effect. So what is Wayne effect? At a very high voltage, around 10 to 5 volt, 5 volt per centimeter, it is observed that the molar conductivity is literally increases, simply because of the dragging effects like this ionic atmosphere, symmetric effect, electrophoretic effect. Such effects are now literally absent due to the presence of high voltage. Now that what Wayne effect is all about. Similarly, like Wayne effect, another effect is there that we will call Debye-Fackenhagen effects. Debye-Fackenhagen effects. Just like high voltage, high frequency AC current also have an effect on the molar conductivity. It is observed that at a high frequency AC current, the molar conductivity found to be increased. That means we expect some changes in the molar conductivity due to the presence of this ionic attraction is exists in the solution. That's literally gone due to this high voltage or this high frequency AC current, which doesn't allow the ionic atmosphere to form. So there is no real time there to this ionic atmosphere to form, or relaxation time increases. So that's the way you can now think what effect now brings by this high voltage and high frequency alternative current. So high frequency alternating currents increases, it's around 3 to 5 megahertz, 3 to 5 megahertz m no mHz, that's why you can represent megahertz, actually increases the molar conductivity, increases the molar conductivity. So what this Wayne effect and Debye-Fackenhagen effect introduced for you, it's actually suggests that if the molar conductivity increases no such high voltage and or no such high AC current, high frequency AC current, it suggests that no it require high voltage or no this high frequency to really break that no ionic atmosphere. Because this actually suggests that no, yes, ionic atmosphere is present in the solution, that has can only be broken at a high voltage or no at a high frequency AC current, that doesn't allow the ionic atmosphere to form. So this is the way we saying that it's an evidence for the existence of no ionic atmosphere which is exist in the solution. Because no, if ionic atmosphere exists there, we expect a molar conductivity to decrease, because no its ions are attracting each other. But this point, this two theory, that is Wien effect and this no Debye Feck and Hagen effect, actually tells you that no, yes, they can able to break such dragging forces no at a high voltage as well as at a high frequency AC currents. So that helps to break this kind of a dragging force. So that's what, that's all about no two important effects that we know just studied, Wien effect and Debye Hagen effects. Next, now is a very important term, so that we will call activity and activity coefficient. Activity. Activity and activity coefficient. So EFFICIENT. Activity coefficient. So what is this activities all about? This is something no student has to understand, because now more often you will hear this word activity, which actually means no effective concentration. Activity definitely means effective concentration. Effective concentration of a particular ion, of a particular component, you can say particular component in a solution. In a solution, we now represent activity as small a. What's the effective concentration one student has to understand? We know we expect when a sodium chloride very dissociate into Na plus and Cl minus. So now 1 mole of NaCl, if it now dissociate 1 mole of Na plus and 1 mole of Cl minus. So we expect now Avogadro number of Na plus ion and Avogadro number of Cl minus ion. But it's observed that no, it's not all the ion which actually contributing to the properties like no molar conductivity. There is a change, because no we already saw the kind of no ion attraction. Both positive negative ions are attracting each other. There will be a repulsive factor between the same type of ions and no like cation anion, there will be a repulsive factor also may exist. So this is very important term that now introduced now that we call activity, which is actually mean the effective concentration of a particular component. It may not be always the same as the concentration that we express. It has some change, because depending on the concentration, at lower concentration, at a higher concentration, the activity of a particular electrolyte may be different, because it's have an effect, ionic attraction and repulsion, everything it has to be considered. Similarly, based on the type of electrolyte, like monovalent electrolyte, polyvalent electrolyte, it has the difference. So that why activity is going to be is more important. Rather than saying molarity such term, we just now shifting to a new term that we will call activity, which means effective concentration of a particular component in a solution, that we will call activity. Let us let us have an electrolyte Ma, which exists in equilibrium to exist as M plus and A minus. So this is dissociation of a weak electrolyte like Me, which is dissociated into M plus and A minus, which are in which are in equilibrium to each other. So ionized form and unionized electrolyte are in equilibrium. Now, how can you write the equilibrium constant? Equilibrium constant we usually write M plus concentration of M plus into concentration of A minus divided by Ma. So in rather than concentration we introducing A instead of concentration. Now onwards we can start thinking about activity of A M plus into activity of A minus divided by activity of Ma. So this is equilibrium constant for you, activity A M plus into this into you can think, and the activity of A minus divided by activity of Ma. So we introduced activity for each component. There are positive charge ions are there, negative charge ions are there. So Am plus into A minus divided by Ama will be the equilibrium constant. This is not, remember, activity is definitely concentration, but now we will call effective concentration. That why we can now think about activity when you talk about concentration. So this is the equation you can remember now to find the equilibrium constant. Now, what is activity? How can you find the activity? If now we introduce the concentration of a particular electrolyte in molality, M is the molality. What is molality? Means the number of moles of solute divided by kilogram of the solvent. So molality, now we will say M is number of moles of solute divided by kilogram of the solvent. So we always know activity is actually it's a concentration itself. So definitely proportional to M. M is there. But now we introducing a constant that we will call a gamma M. Where gamma we will call activity coefficient. Activity coefficient of a particular component. So now what is M is molality is activity. So activity is we can say is a product of activity coefficient and the concentration, the term that we use here. When I use molality, so molality is it's a concentration term. So A we define like this: A is equal to gamma M. So it's a product of activity coefficient into M, that is molality here. So activity and activity coefficient, these terms are important because an electrolyte in a solution have different behavior, especially considering the kind of attraction and a kind of repulsion and the concentration and the kind of electrolyte that we use have changes depending on these kind of conditions. So activity will give you a effective concentration of a particular component in a solution. So that's an equation very important. A is equal to gamma M. So by using that now you can change the above equilibrium constant equation. Instead of A you can now use gamma M, right? So for a cation we can use gamma M plus into M plus. So A is equal to gamma M, right? A is equal to gamma M. So instead of A for a cation we use gamma plus M plus into gamma A minus A minus divided by, instead of A, gamma Ma into gamma Ma into Ma, molality of Ma. So this is now we just introduced two important terms. A is activity and gamma is the activity coefficient. So these are the two terms that you can remember related to the related to a solution. Where now onwards you will listen this activity quite regularly. Now it's observed that it's not easy to find the activity of a particular component like cation. I will say if I want the molar conductivity, the activity or activity coefficient of a particular component is very difficult because NaCl always dissociated as plus ion and minus ion. Such cations and anions will be there. So it's very difficult to find the activity coefficient of a particular component or no particular cation or anion, we will say that why we introduce another term that we will call mean ionic activity. That's what we call mean ionic activity. The terms are no small difference only. Mean ionic activity, which we know we can write like this. For a electrolyte Ma gives M plus A minus. No activity you can now introduce as A plus A minus. A plus A minus, which is equal to A plus or minus whole square. A plus or minus whole square. Where A plus or minus we will call mean ionic activity. Now, why this is introduced? Because it's very difficult to find the activity of a particular component. So we actually using this mean ionic activity, considering the ionic activity of this this cations and anions. We introduce a new term. Now we actually saying that product of activity of cations and anions. So A plus into A minus. So A plus into A minus, A into A, we can say A square where plus or minus also there. So A plus or minus whole square, which is will be A, where A plus or minus we will say that it is a mean ionic activity. Mean ionic activity. So now let us now change that equation for a electrolyte like MxAy. MxAy. How can you write the dissociate as X moles of A is there, X M raised to Y plus Y A raised to X minus, because Y plus will be the valency, the charge of this will come here, this will come here, so that will be the charge of this cation, right? And X will be the charge of this anion. This is cation, so Y plus, and this is anion, so X minus. So this is the way now you can just change that equation for a electrolyte type MxAy. It will dissociate as X M Y plus Y A X minus. So now let us change that equation by considering A activity will be equal to A plus raised to X into A minus raised to Y. Now this is the way where X and Y for an electrolyte depending on the coefficient of these electrolytes of each component, like cation and anion. So we can say A plus or minus raised to X plus Y will be the activity of a electrolyte type of MxAy. It's not maybe always a monovalent electrolyte, it's maybe polyvalent as well. So we can find the activity using this equation A plus or minus raised to X plus Y. So that's the way you can find the activity of a polyvalent electrolyte. So X plus Y, now you can easily understand what is the depending on the type of electrolyte you can find X and Y. So X plus Y will give you the activity of a particular electrolyte. Now for comparing the molar conductivity and other concentration everything, we introduce another term. So this is the fourth term that we are going to discuss, that we will call mean ionic activity coefficient. Mean ionic activity coefficients. So now what is mean ionic activity coefficient is all about. Now let us have that equation A is equal to A plus raised to X, A plus raised to X into A minus raised to Y. This is the equation we just saw, right? So we know A is equal to gamma M. So we can write A plus will be equal to gamma plus A is equal to gamma M, right? So A is equal to, now let X moles is there, so X M raised to X into A minus, you can write gamma minus ym raised to y. Ym raised to y. So gamma plus xm raised to x into gamma minus ym raised to y. So now we know a is equal to, remember a is equal to gamma m. So where m is the molality, x is the coefficient of that particular component. So a is equal to, you can write a plus raised to x into a minus raised to y. So we introduce a is equal to gamma m, where no, if that's for a monovalent electrolyte. For a polyvalent electrolyte, no, x and y also coming into play. So gamma plus xm raised to x into gamma minus ym raised to y. Now let us reshuffle it and make it equal. No, so x raised to x, activity A is equal to x raised to x into y raised to y. This is now one part, you can write like this. Similarly, gamma plus into gamma plus raised to x into gamma minus raised to y. That's another part. Then m raised to x plus y. So this is the way you can now write the equation for activity. Now having seen like this, don't get confused. See, you write it, you will understand. So x raised to x into y raised to y into gamma plus raised to x into gamma minus raised to y into m raised to x plus y. Where now let us simply simplify it. Or now you can write activity which is equal to a, which is equal to x raised to x into y raised to y into x raised to x into y raised to y into gamma plus or minus m, gamma plus or minus m raised to x plus y, gamma plus or minus m raised to x plus y. So gamma plus raised to x into gamma minus raised to y is nothing but gamma plus or minus x plus y, gamma plus or minus raised to x plus y, and m raised to x plus y. I just combine that. A is equal to x raised to x into y raised to y into gamma plus or minus m raised to x plus y. Now let us have that word gamma plus or minus, that we will call yes. Yeah. Yes. So now gamma plus or minus we will call mean ionic activity coefficient. So we learned 4 terms today. So let us write the terms only because each have very minute difference, right? So what is A? A is the activity of a particular component in a solution, and gamma is the activity coefficient, and A plus or minus, that we will call mean ionic activity, and gamma plus or minus, that we will call mean ionic activity coefficients. So these are the 4 terms that we introduced today, okay, related to activity. Now it's more easier to find the activity now using this activity coefficient. We know A is equal to A plus or minus raised to x plus y, right? So if a particular electrolyte Ca, anything that you can do, CaCl2, BaCl2, barium chloride, it will be no activity you can find by A plus or minus raised to x plus y. No, it will be 1 mole of barium and 2 moles of chlorine. So it will be x plus y will be 3. So depending on the electrolyte, you can find the the molar the activity of a particular component using this equation. A is equal to we know A is equal to gamma plus or minus. So A, we can write A is equal to gamma m. So in that way, gamma plus or minus whole cube raised to m raised to cube. That will be the activity of a particular electrolyte that we are talking about, having x moles of cation and y moles of anion. So we can have A is equal to A plus or minus whole cube for a particular electrolyte like this. Or no, we can say it's not monovalent, it's polyvalent. So A plus or minus whole cube. This is the way you can find if you have the mean ionic activity coefficient and molality. You can find the activity of a particular electrolyte. So that's the way now you can you introduce the 4 terms, that is activity, activity coefficient, mean ionic activity, and mean ionic activity coefficient. So now out of these 4, now this is the one we are actually using to compare the electrolytes. Now the behavior of an electrolyte in a solution is actually introduced by this factor, that is mean ionic activity coefficient. To reach that, you have to discuss the 4 terms. So more often mean ionic activity coefficient going to be actually used to compare the effective concentration of a particular component in a solution. It's found that it has a different behavior in a solution based on the concentration. Let us plot a graph between mean ionic activity coefficient versus molality. Now the graph is really interesting. Let it be, this will be 1 molar. Now concentration will be 1 molar, and this is 0.8. This is 0.6. That means the activity mean ionic activity coefficient decreases down, and it's 0.2 like that. So this is the way we plotted mean ionic activity coefficient on the y-axis, and in the x-axis I plotted concentration. And now different behavior you observe that it's for a NaCl it is just like this, and for a CaCl2 it's different, it decreases, reaches a minimum value, then there is an increase. And for another electrolyte it will be just like this, and another type of electrolyte which is it's coming decreasing, and now it's going steeply like this. So now different electrolytes behaves differently. That's the point. Now you can understand if you plot a graph between a mean ionic activity coefficient versus molality. So what does it suggest? It suggests that at lower concentration and at high concentration electrolytes behaves differently. The effective concentration seems to be different at lower concentration and higher concentration. At lower concentration you can see most of the time it's on the higher side. That means at high dilution, yes, the effective concentration of a particular component is definitely high. They effectively contributing to the properties like this molar conductivity, such properties they effectively contributing. But as the concentration increases, you can see moderate concentration at a higher concentration it has different behavior. For a electrolyte like CaCl2, look at this, the curve for one particular curve is decreases reaching a minimum, then increases. So at moderate concentration you can imagine somewhere here, and at a very dilute solution molar conductivity, the mean ionic activity coefficient is very high, then it decreases, then at higher concentration it seems to be increases. So that's the way you observe in the case of CaCl2. For a lanthanum chloride, NaCl2. It's just a similar type of graph, but NaCl you can see it's different. Where higher on the higher dilution, then it decreases, then a slight increase you can see for now this zinc sulfate. This is actually again a different. So depending on the charge of the cation and anion, depending on the concentration, the effective contribution of a particular component in the solution is different. That's a point you can learn. Each ion behaves differently depending on the nature of the electrolyte. So mean ionic activity coefficient actually sums up that thing. You cannot simply say a particular electrolyte or a strong or a weak electrolyte behaves like this. No, you cannot say, because the kind of attraction between cations and anions and the kind of repulsion between the ions, everything will come into play when you talk about their contribution to molar conductivity such properties. Because now the effective concentration is you have to consider that is different for an electrolyte at a dilute solution, at a moderate concentration, at a high concentration. You can see it's different. Why maybe the molar conductivity increases, why the mean ionic activity coefficient increases at a higher concentration? There you have to imagine the kind of repulsion factor will be higher, because cation and anion repulsion factor will be higher at higher concentration, which means now ions are more freely can able to move. They effectively contributing to the properties. Effective concentration become higher. At dilute solution, a simple answer, because ions are free to move, they effectively contributing to the properties. So these all are now effective concentration in a particular solution, considering the kind of attraction repulsion exists in the solution. It's different for a different electrolyte. That's the way you can understand. It's not you can sum up one thing. Okay, it's just one particular electrolyte behave like this. It's even one particular electrolyte at a different concentration behaves differently. The effective concentration is going to be different. So that is the very important term that we introduced today. That is we call mean ionic activity coefficient. So these are the terms again will come in most other parts. So try to understand these four terms: activity coefficient, mean ionic activity coefficient. So these four terms we introduced today. Learn it. It's very important to understand. Okay, thank you.